Welcome back to Precalculus. So we're going to do a couple of examples now, that third and fourth from the previous video. So the first type, which is the third one in this one, is going to be combining two forces. You're told what the resultant force magnitude is. We're trying to find the angle between them. So let's make this into a sketch. Let's say you have something here that you're tugging on, okay? So you're tugging on it with a 3,000 pound force. And the book does say, for simplicity's sake, just assume the first vector is along the positive x-axis, or either vector. I'm just going to do the first one along the positive x-axis. It really doesn't matter, but it'll make it a lot easier. So I did that one in red. And the 1,000 pound force, I'm just going to guess. I don't know what it's going to be. I'm just going to guess here. Again, it's shorter than this one. So imagine you are... that's 1,000 pounds. Imagine you're pulling at like a tree stump, okay? The blue dot there is a tree stump. And you have a green car pulling with 1,000 pounds of force, and your friend shows up to help with his 3,000 force red car vector. So when the tree stump finally comes out, what will the path of the tree stump be? Well, I'm going to argue that it's going to go somewhere in between, but probably closer to the stronger vector. So something like that. And they say this is really what we're doing when we do this, is we're applying 3,750 pounds of force. Well, how do we make sense of this? These three vectors are coming from one point. Do I know the angle between any of them? What is the angle between them? Well, the angle between the original vectors is actually this angle right here, right? So how are we ever going to get that yellow angle? Well, the key is something we talked about in the very first 6.3 video, is when you add vectors, you want to add them head to tail. So I did my 3,000 pound vector, and I'm going to redraw the green vector right here, and I did this on purpose so that it would meet, and they will. That's the whole point. Because remember, when you add vectors head to tail, you can connect the resultant, and so that is resultant. The question is, my yellow angle is gone, or is it? Couldn't you have extended this red line out? Just kind of do it like this. If you did, notice that yellow angle is actually the same as this yellow angle. How do we know? Well, the two green vectors are the same length, but even more important than that, same slope or direction. So since the two green lines are parallel, those two yellow angles are what we call corresponding angles, where they're always congruent. Back to geometry there. So my task is to find the yellow angle. I'm going to draw this again just to kind of get rid of all the excess. Really, this is a triangle problem. That's 3,750. This is 3,000. This is 1,000. And what angle are we looking for? You're like, I'm looking for this yellow angle here. But how can you get that little angle on the outside? We'll call that theta. No, let's not call it theta. To be consistent, let's call it phi. You need to find this angle first, theta. If you get theta, you can get phi, right? So theta is that obtuse angle, and we know that theta and phi are supplementary. So what method are we going to use to get theta? Think back to 6.1, 6.2, law of cosines. And I'm not going to spend a lot of time on that, but I want the angle opposite the 3,750 length segment. So I will just set this up. And I do not have an answer here, so I will quickly do this. And we are expecting it to be obtuse, and it is. You can check me on this. I'm getting 132.62 degrees. So remember the question was, what's the angle between the vectors? It's technically that phi. which is 47.38 degrees. So that original phi, which was the gold or yellow there or there, is at 47.38 degrees. Really nice technique. Once you've seen this, you know you're going to do law of cosines once, and then you're going to find its supplement. That's it. So, okay, the final type of problem is the one that used to be long. And then a few years ago, I don't know, students convinced me my way was too long, and it was just not the smartest. So I've finally given in, and I have much more of a, physics type approach. We're just going to use our calculator. We're not going to try to use trig identities, even though the ones in the book you could. So I'm going to make up an example, kind of like number 87 in your book, and it's going to say this. You have a 40 Newton vector applied at a 32-degree angle from the positive x-axis. You have a 50 Newton vector applied at an 85-degree angle from the positive x-axis. Let me write that a little better. And you have a 75 Newton vector applied at a 161-degree angle from the positive x-axis. I used to say sketch them. No, you don't need to sketch them. So here's how you can do this very fast. In the end, you might think this is the easiest problem we do. So I'm going to find the x component of the vector. The x component of the 32-degree angle is that. And I need to add it to the x component of the 50 Newton vector. And I need to add that to the x component of the 75 Newton vector. That's my x component, that sum. Then I need to find the y component of the vector. I'll take the same, I'm going to basically write the exact same thing, but instead of putting a cosine, I'll be putting a sine. No comma yet. Sine 160, whoops, okay. Trying to look at too many things at once. So that should be, that should be 160. Okay, am I going to mess up any more times? I'm going to just copy that down. Instead of cosines, I'm going to write sine. 75 sine. I don't know why it keeps going off on me here. 75 sine 161. Wow, that was a trouble. Okay, so let's check it. 40 cosine 32, 40 sine 32. Just gonna mix up the colors here. 50 cosine 85, 50 sine 85. 75 cosine 121, 75 sine 161. Wow, this problem I'm butchering. So same magnitude, same direction, but the x's have cosines, the y's have sines. Put it in your calculator. I'm going to put in just the cosine one first. 40 cosine 32, close parentheses, plus 50 cosine 85, close parentheses, plus 75 cosine 161, close parentheses. I'm going to check it. They all have cosines, 40, 50, 175, 32, 85, 161. It looks good. I'm getting a negative. Is that alarming? Nah, not really. That just tells me that the 75 cosine 121 actually, and is pushing us into negative x direction. So that's okay. So the whole thing is a negative 32.63. I'm going to store that in my calculator as x. I want to keep the best approximation I can. Now, instead of retyping all those other ones, I'm going to hit second enter, or you can up arrow if you like. And I'm going to go and change just my 3 cosines to sines. I don't have to type anything more than that. And I get 95.42. Store that in for y. Okay. Now, really, that's all I need, those things. So I've gone from three magnitude direction pairs to 1 component form pair. Now I want to take this back to magnitude and direction. the way I do it is first finding the, so this, we'll call this R, finding the magnitude of the resultant. Now that I have those fancy X's and Y's, I can just do this. We'll put that in our calculator in a moment. And then to get the, so there's the magnitude. To get the direction, I will make sure I store that in for Y. To get the direction, I'm always going to advise you to make a sketch. You don't need to make a sketch until this moment. So I'm going negative 32 up 95, something like this. Why am I writing that down? Good place to put my X there. And Y there. So the resultant is there. And you can see, again, why the Pythagorean theorem made sense. To find the angle, I need to first find theta. But when I get theta, how's that going to relate to phi? Here's my axes. Let me try that again. Then my phi will be this angle right there. Phi. That is my resultant. Can't draw. Okay. So to get phi, I need to find theta first. So the tangent of theta is y over x. And then I can just second tan that. I'll just write that out. Okay, so plug this in your calculator. Plus y squared. I'm getting 100 for my resultant. And you might think to yourself, is this reasonable? Yeah, I guess. It's a little lower than I expected, 100.85. We don't have any units, so we'll just leave it like that. And then this one is, again, second tangent. And I'm just putting y divided by x in my calculator because it knows what y and x is. I'm getting, oh, okay. It's getting a negative angle. So because my x was negative, so if you want, you could just, I would just drop the negative. If that concerns you, you could say, say negative x, stow x, and then do it again, and you'll get positive 71.12. So what I did was I overstowed my x, making it positive. By saying negative 71, they were just trying to get me in the right quadrant. But of course, my answer is not theta, it's phi, and I want the supplement to that, which is 108.88 degrees. So there's my magnitude and direction, and I strongly advise that technique. This right here is such a time saver doing this. So 3, 4 vectors, not a big deal. And if you were writing a computer program to do this, very easy to do that way. If you're using trig identities, it just works in so few cases, like the book does. So if you look in the back of the book and you see radicals, don't worry about it. I'm fine if you do decimals. So that wraps up 6.3. It is a long one, I know. So congrats for making it through. 6.4 is